So far in our reviews, we've done a single pendulum, double pendulum, and triple pendulum using the kinematics table. We then took a double pendulum, and as we see on the left, we used constraints to turn into a slider crank. So the velocity of the slider is the VQX from the kinematics table that says the slider can only move in the X direction in this particular example, and there's a constraint that VQY is equal to 0, meaning the slider can't lift up, move up and down. We then took a triple pendulum from the kinematics table, and again, you've seen it in class and the review. And we said at point R, remember B for base, P for point, then we continue Q, then R. R, what happens in a 4-bar, is pinned. So yes, it can rotate around pin R, but it can't translate. There's no translational velocity. So we have two constraints, VRX equals 0 and VRY equals 0. And similarly for both, we have a solution if we need acceleration as well, and that's back in the review for those. But back in the first week of class, when we were developing these kinematics representations, looking at something called mobility, right, your degree of freedom, where a slider crank and a 4-bar each have one mobility, which is 1 degree of freedom. We can look at it as you only need one actuator to move it. We said you might have a point of interest somewhere else. That's important. Typically, it's called an offset point or point of interest, which I have here as labeled with the letter S. And so I'm going to zoom in on the 4-bar because I have the angles on that one. Let's take a look. So as in the past, from B to P, the angle, which is a function of time theta, is written with respect to the horizontal axis. The same thing, phi that's squeezed in there, with theta, we have phi, as well as psi. Just remember how that's defined, and of course counterclockwise is positive, and its lengths between the pins are R1, R2, and R3. But I might have a point, a different point that I care about. And again, I can develop this for link 1, link 2, link 3. For consistency, I pick link 2 since I can see it on easily on both the 4-bar and the slider crank. So I have this point S. Its distance is R4 from P, and its angle is gamma. Now, gamma is fixed because it's defined as the angle between that line between P and S and the line between P and Q. So gamma is constant, but phi is not, because these mechanisms do move. Going back to the slider crank, where I didn't squeeze in the theta and phi, it's a little bit hard to see if I had, but there's the gamma in there as well. So what do we see again? They are both on link 2. So how do we handle this offset point or point of interest, whatever you prefer to call it, point S? First step, first 3 kinematics tables for 4-bar, 2 kinematics tables for the slider crank, and then you must go ahead and use these equations. So for the slider crank on the left, we have them here, hitting the dead spot, and on my screen, and on the 4-bar we have here, and as I said, there are the equations as well available for the acceleration. Right? Acceleration of sliders is AQX, its constraint is AQY equals 0, and on the 4-bar, your constraints are ARX equals 0 and ARY equals 0. So we have those from the kinematics table, and I just put them here to have them in front of us again. Make them a little bit smaller there, and I'll pause there for a moment if any of you are just copying off your screen. But what do we have? We have the velocity at R and the acceleration at R. And we can see in there, buried in there, if I needed my earlier ones, we had captured the velocity at P. So if you remember, this came from your velocity at P. If you look back in your notes. Then we moved on to Q, which added this. And then we moved on to the full R. So we added those components. Similarly for the acceleration, if you remember, this was your acceleration, your APX. This was your APY. Then we went to Q, so we had to add P plus the Q term. So these two together, these four terms, these two things circled, set circled, would be your Q, adding these over here for the Y component. So these four terms all together would be your AQ Y, and to get the full AR, we need all these terms. So we add these two. So you'd have your 6 for your ARX and your ARY. So you've seen that in the past in class as well as review and for homework. So we've done all that, we know that, and we've written our equations, our constraints equations for the slider, crank, 4-bar, whatever it is we want to do. So now we just need a point of interest. Then it's pretty simple. We take out a kinematics table. So if this was a slider crank, you'd have 3 total. First link, second link, and point of interest. 4-bar, 4 kinematics table. First link, second link, third link, and now I need one for the point of interest. So if you remember back when we introduced it, what did we say? Focus on the link you care about, you draw right on the table. What do I care about? I have this link from P to Q that also has that point S on it. We have the lengths R3. We have the lengths R4. Let's check that here. Oops, sorry. That's right, R2. I knew that looked wrong. We have the length. I will fix that. Knew something was bothering me there. There we go. We have the length R2 from P to Q. We have the length R4 from P to S. We have phi and we have gamma. Let's just remember the link spins, so phi is a function of time. But gamma is constant, is just within the link itself. What is the angle between those two lines? R3, which is, it says R4 now. I'm sorry, R2. Try to say that better. R2, that spot, R2 and R4 are constant links, and some of the other reviews will have links that move. Okay, so hopefully I fixed all those issues. We said the first 3 lines here are just the worksheet to get set up. Well, we're still in an inertial frame, meaning JK, my coordinate system does not rotate. It does not mean the link doesn't rotate. The link does rotate, but the coordinate system does not. So let me zoom in on this a little bit. And so the angular velocity is 0. The angular acceleration, alpha, is 0. You can see I changed the subscripts, right, to make that omega sub p and alpha sub p. And then a displacement vector from S to P. So that's this vector right here. So what would that be? So its length is R4. Cosine gamma plus phi. R4 sine of gamma plus phi to get us back to the horizontal and 0. Do we recognize these other lines from our early kinematics tables? From our first kinematics table, this is your VP, and this is your, oops, sorry, not alpha, A, P. So those are just off those tables, and we also saw those equations right up here, right? There's your VPX, your VPY, your APX, and your APY. So hopefully you're getting really good at those. And remember, we've said in class about 1 billion times, I would say by now, right, if we know this, 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 and this, the rest is just math. Well, there's still no omega because we're doing inertial frame. These are 0. Can't get easier than these. No alphas. These are 0. Scroll up. Hopefully stay out of the dead zone on the screen. These are 0. So what do I have left? All I need to do is take a derivative of this line to get this line, and then the derivative of this one to get that one. So I would have chain rule, maybe next chain rule and product rule, and that's it. And why am I doing that? To get the velocity at S, my point of interest, or offset point, whatever you want to call it, and my acceleration of S. Oh, there's silly me. So let's take the derivative. So what is different here than what we've done before. So the derivative of cosine is minus sine. So what's the derivative of that gamma plus phi with respect to time? Well, gamma is constant. So all we have is a phi dot. Similarly here, we have R4 cosine of gamma plus phi, and it's just phi dot, because gamma is constant. And that's it. Right? We know what theta dot, phi dot, we know all those terms, we've had them before. And so this here, this is equal to, let me pick a different color here, see if I can squeeze in. That's all VSX, right? Very hard to read there. These three terms would be equal to a VSY, and because we have nothing in the Z. Very similarly, we have the same thing going on here. So we have, at top, I have first term, two functions of time. This is a function of time. This is a function of time because all one's constant. Oops, sorry, wrong line there. This is a function of time. And this is a function of time. And similarly here. Sorry, I did the wrong line when I zoomed in. So what do we have? If I hold the sine of gamma plus phi constant, I would have minus R4 phi double dot, so my angular acceleration, sine of gamma plus phi. Now I hold R4 as constant anyway. I hold the phi dot constant. The sine becomes cosine of gamma plus phi. And then with the chain rule, I get another phi dot, so that's squared. Same thing here. Hold the cosine constant, so I have R4 phi double dot of cosine gamma plus phi. If I hold the R4, well, R4 is constant, the phi dot constant, sine becomes minus sine of gamma plus phi. If I'm using the product rule, but now I have the chain rule, phi becomes a phi dot, so that's the phi dot squared because I already have one, and that's 0. And if I zoom out a little bit here, all these terms, and most of them are 0, but all these terms, that's what. That's equal to my acceleration s in the x direction. All of these are my a, s, y, and if I needed these, 0, but this is a, s, z. So what do we have? We have a velocity and acceleration at a offset point or point of interest. Let's see if we have enough information to solve it. Let's just say we're looking at the 4-bar, because that has more stuff in it, so it's probably a little bit more interesting. What are the variables? We've done this before. If I scroll back up, we had R1, we had R2, we have an R3, now we have an R4. We had a theta, we have a phi, we have a psi, and now we've added a gamma. We have a theta dot, we have a phi dot, we have a psi dot. Gamma is constant, so it stops there. If I'm looking at the acceleration terms as well, I have a theta double dot, a phi double dot, and a psi double dot. So what am I missing for a 4-bar? Let's see. I think I got it all this time. All right. So how many equations do we have for a 4-bar? We have 2 if I'm doing the velocity. If I'm doing the acceleration, I have 2 more. Well, what do we know? We assume we have the geometry in front of us, physically looking at it. So we know the length R1, we know the length R2 between the pins, R3 between the pins, the length for R4. Again. We look at least one configuration, so we know the angles, theta, phi, psi, and gamma is constant. So if I start with the first two equations for velocity, the vrx equals 0 and the vry equals 0, that's two equations, two unknowns. I only need to know one thing. Let's say I know the crank on the left, the theta dot. I can solve for these two. If I want to know acceleration terms, I would need to know one more piece of information because I have two more equations. ARX equals 0, ARY equals 0. So if I assume, for instance, I know that first crank on the left, I know this, I can solve for these two. Traditionally, I would do all of this here, whatever I need, before I would solve these. So think about it. Let's come back now to why we're doing this lesson, this review. If I look at VS, I already know R1, I know theta dot, I know sine theta, right? So I know theta, so I can find sine theta and cosine theta, right? I've already found phi dot, I know all that. So what do I need to know for VS? That's new. For my normal 4-bar, I just need to know R4 and gamma. That's it. And if I zoom in here on the acceleration term, right, if I already solved my 4-bar, so I know that initial stuff, what else do I need? Just R4 and gamma as well. So this is an example of a point of interest or offset point on link 2. But if I had it on link 1, I would just do a new kinematics table on link 1. If I wanted for 3, I can do another kinematics table for 3 very similarly. Any questions, like usual, come ask one of your faculty.